before we will be able to talk a bit about the more exciting subject of support vector machines, we first have to talk about hyperplanes and linearly separable data. So if you already know what hyperplanes are, feel free to skip the first bit, but it might be a good reviser anyhow, even if you do. So the first thing is, what is a hyperplane? It's a common term in mathematics to describe a kind of lower dimensional space in a higher dimensional space. In particular, for a plane, it's a linear space. But the idea is really that I have one constraint in a kind of a p-dimensional space. I have one constraint, and this transforms my p-dimensional space in a p-1 dimensional space, and this space is called a hyperspace. And it's in particular, as I just said, if it's linear, then we call it a hyperplane. So the kind of more general expression for a linear relationship in kind of p dimensions is we have a kind of intercept, and then we have the p variables, each one with its own slope. And if we set this thing equal to 0, then we have a p-dimensional hyperplane. Now in 0 dimensions, we have so in 1 dimensions, the hyperplane is just a point. In 2 dimensions, the hyperplane is a line. And in 3 dimensions, the hyperplane is an actual plane. That's where the name comes from. And then, well, in 4 dimensions, it's harder to imagine, but people just generalize the idea of hyperplane. It's basically generalizing from 3 dimensions, which is what we are most used to. So we're used to 3D, so we can think about planes, and then we just say, well, for anything higher, we just call it a hyperplane. But it might be worthwhile to make a little picture here and see how it comes about. So first of all, so here we have this relationship. We might just as well write it down. So f of x was some, which variable did I use? Beta. So beta 0 plus beta 1x. This would be the one-dimensional case. And then this would be 0. So in 1D we see this thing is just a point. We will have x equal to minus beta 0 over beta 1. This is just a point. So here we have my one-dimensional line, x, and then the hyperplane is just a point here, namely this point here. So this will be kind of 1D. Now we can do 2D. In this case, this relationship f of x would just be kind of beta 0 plus beta 1 x1 plus beta 2 x2, and this equal to 0. I should have maybe called this x1 before. And now what do I have? The kind of relationship is simply a line. As I can see when I solve it, maybe the most common way of solving for the line is if I solve for x2, I would have kind of x2 is equal to minus beta 0 over beta 2 minus beta 1 over beta 2 x1. This is kind of the relationship just solving for x2. And if I can plot it now, so here I had just one direction x1, now I have two directions x1, x2, and now I have my hyperplane is just a line here basically. And now for 3D, the equation looks like this. I have f of x equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. And if I use like 3 vector notation, I could also say obviously beta 0 plus beta times x vector, where this would be just 3-dimensional vectors here. Obviously this equation should be equal to 0, and so I was just defining this is beta 1, beta 2, beta 3, and so on for the other one. So now obviously what I will have is I have a 3D space, x1, x2, and x3, and this thing will just be a kind of plane in this space. So this is why it's called a hyperplane. Now I have not yet derived for you why this is a plane. I just wanted to realize obviously kind of this is a point, this is a line, now it's a plane. So what's the easiest way of seeing that this equation here, which can be also written as this equation here, what's the easiest way of kind of seeing that this is a plane? And I think one of the best ways of writing it, you might know it from your earlier calculus classes, is that if you think of it, if I have the plane here, this is my plane, and I'm just looking right at it. It's easier to draw it. You see, I'm not that good at drawing those 3D pictures here, so I just draw it looking right at it. So the plane is lying here, and now one way of drawing it, there will be one vector which kind of holds the plane in place. Let's just call this vector A. So here's the origin of the coordinate system, 0 or O. The one vector holds the plane in place, and there will be another vector which is orthogonal to the plane, orthogonal in all directions. It's like here, I have this plane, and now I have this vector orthogonal. If I turn the vector, I will turn the plane around. So you can see how kind of a single vector defines the plane, because it's always orthogonal to the plane. So a vector orthogonal to the plane defines the direction of the plane. But then you can still shift the plane around, and by having a kind of vector A, it holds the plane in place, basically. And now you can see that actually any point on the plane, any point x sitting on the plane, actually obeys the above equation here, because this difference here is just x minus a. So x minus a is this vector, but I know that this vector lies in the plane. If it connects a and another vector which is inside the plane, an arbitrary point x which is inside the plane, then this difference vector x minus a lies in the plane and is thus orthogonal to beta. And I know that two vectors are orthogonal if the dot product is 0. So I have something like x minus a times beta equal to 0 here. But this is a relationship I can easily solve. I can write it as minus a vector times beta vector plus beta vector times x vector is equal to 0. And now if you define this thing here as beta 0, you see it's exactly the same as this equation above here. This is just for you to revise quickly the plane relationship. This is something that's done in calculus. Some people do that in high school, but it's just to remember, like a normal vector defines a plane. I just need the direction of a plane. If I have another vector which pinpoints where it is, I have the exact equation of a plane. And I can also write it in this. This is sometimes called the normal form of the plane here. Because it has this normal vector beta here. So this is just a general relationship for a plane, and hopefully we have seen some understanding of those examples here. We have for a 1D space, I have a point separating a hyperplane. In 2D it's a line, and in 3D it's a plane, and generically this is the kind of plane relationship here. Now this works for 3D, but you can think of this vector notation as I've written it down. It actually works exactly the same for higher dimensions, higher than 3. You still have those orthogonal relationship, and the equation is exactly the same, and the interpretation is also exactly the same in terms of having this one vector which is orthogonal to the other one and one linking the plane. So this relationship, I've written it down for 3D. It's easier to think about it for 3D, but using this vector notation, it holds also for any higher dimensional vector. So just to make this bit clear. Now, so this was just a kind of quick recap on kind of hyperplanes and how to define a plane in general using vector notations. So now we are going back to our classification problem. So as previously in our classification problem, we have some predictors here, p predictors, and obviously we have our response variable y, where this response variable can have two labels now. Before we used for the labels 0 and 1, usually for like no spam and spam, no cancer and cancer. Here we like to use -1 and +1 instead for the labels. In principle, we could choose any numbers for the labels. It's just we saw that for logistic regression, 0 and 1 was a smart choice because it made the math very simple. If you recall, in this in the log likelihood, we had this p to the power kind of yi and 1 minus yi, so kind of 1 was always there or not there. So there was something special about 0 and 1 which made the math particularly simple. Now for the support vector machine or support vector classifier, it's the math becomes a little bit nicer if we choose labels -1, +1. Otherwise, there's no reason why I cannot use any other label, but it's just the math comes out a bit nicer if I use +1 and -1, and we'll see in a little bit why that's the case. Before we get to this, I just first want to talk a little bit about linear separable data. So linear separable data is effectively some data in some space which is such that I can find a hyperplane which kind of divides the space in two halves, so that kind of one type of the data, one label of the data is only on one side and another label of the data is only on the other side. So if I had a space, a predictor space, and I have some points which correspond to Cancer, some other points which correspond to no Cancer, if there's a plane which can cut right through the space, that everything on one side is Cancer, everything on the other side is no Cancer, then I call this a separable hyperplane. So say here would be one label here, say Cancer. Here would be another label, no Cancer. In this case, I can find a plane. Oh, I should have maybe used the other. I can find a plane such that on the one side there's only Cancer, on the other side there's no Cancer, and this is called a separable hyperplane. And the data is called linearly separable because there's a linear hyperplane which separates the data. Hyperplane, linear hyperplane is a bit redundant. It's just a hyperplane which separates the data. But just to let you know, it's not always possible. In reality, it's hardly ever possible. I mean, you can see already here, imagine I had data doing this. There's no way I could find a separable hyperplane in this case. But for now, let's just assume we have this type of data. Let's come up with a very simple model, and then let's just worry about later how we can kind of generalize this model to deal with the more realistic cases where I do not have linear separable data. So here's some examples. So here I see some data. Again, I have like kind of no Cancer and Cancer data points in green and red, and now I have some kind of separating hyperplanes here. So this data is linearly separable, and I can find some plane. So here are several examples. This one here is one example of a plane, this one as well, and this one as well. And kind of, well, the second one isn't very nicely drawn, but well, you got the point here. This one here, this one here. Those are three different hyperplanes. I can draw many more. I can draw this one here as well. They are all possible hyperplanes which separate the data. So this is linear separable data, but one thing we want to talk about now is kind of, is there maybe one type of hyperplane which is kind of better than others, and this is what will lead us to what's called the maximum margin classifier, which is what we want to talk about